Yes, so I'm Marc. I work at Belfort. We're trying to make FHE usable by making it easier to use and making it faster so that it can apply to more use cases. And today, so I entitled it FHE Applications, the Need for Speed, because in the concrete setting, if your application takes 10 hours or 10 seconds, like it makes a large difference between being usable or being not usable. So I'll be happy to take questions during the talk. So if you want to raise your hand, don't worry about it. And yes, and many of the slides that I'm going to present, you're going to see are going to have, you're going to feel like you're in some sort of parallel universe with respect to 1 hour ago, because many of the things that I'm going to say are going to relate to what Wouter was saying, but kind of in a different context, because I'm going to focus mostly on the CKKS scheme. But first, a few words about Belfort. So it's a spin-out of COSIC. So at the end of the slides, I have a slide with the team members. You're going to recognize a few of them. But yes, so it was spun out last year, and already we have a POC. We had a POC with Swift, and we have Google as our first paying customer. So we're already starting to see traction, and we believe that there's, product market fit, like there's an appetite to be able to do these computations in the encrypted domain. So very briefly, right, what's the idea? The idea is you have the client who has the private key. He's going to encrypt the data, send it to the server. The server does the computation, does not see the data, and then shares the final result with the client. The client has the private key, can decrypt the result, and obtain the unencrypted result. So at Belfort, we have two product lines. So the first one on the left is based on TFHE and is using FPGAs. So that's actually the commercial version of the FPT accelerator that you saw in the previous presentation. And yes, so if you want to write your FHE program using the TFHE scheme, it's better suited if you need like bit level precision. And then you have another scheme, which is CKKS, which is the one I'm going to talk to you about. This one we accelerate on GPU because it's a better suited platform. And CKKS, the difference is that it has an inherent error associated to it. So that means that it's going to be much more difficult to get like bit level precision, but it has much higher throughput. And if you are okay with accepting a little bit of error, which is typically the case for machine learning applications, then you get a much higher throughput and your application can go much faster. So yeah, I'm going to talk about a few of the use cases that we have. And so what's our philosophy or the approach that we're taking, right? It's a little bit similar to what Wouter was saying. So we want PyTorch to be our front end, basically. So we should have that the developer can write his PyTorch model, right? It's a machine learning interface that is very familiar, that is kind of an industry standard. And then we're going to compile it down to one of our hardware accelerator. So either FPGA if you want TFHE, GPU if you want CKKS, and right now we're also working on an ASIC, which would also target CKKS. So we have kind of 3 layers that you can think of. So we have hardware, algorithms, and applications. And I want to talk about improvements and work that we've been doing on each of these 3 layers. But first, let me give you like some maybe motivation as to why we need these hardware accelerators, right? As I said, so you have here, you have for ResNet, who has heard of ResNet here? Who knows what, so, okay. ResNet is it's kind of a benchmark image classification neural network. So it has, we're talking here about ResNet 20, meaning that it has 20 layers, and it was kind of a breakthrough model, but like maybe 10, 15 years ago, and it's been used as a benchmark, right? Because it was kind of one of the first models that was doing image classification, and that was giving pretty good results. And you can see, like, the time is in milliseconds, and the first ResNet implementation in CKKS, that was 10.8 million milliseconds. And to give you like an idea, if you don't like to do the math in your head, like the 2.2 million milliseconds, that's roughly 35 minutes, right? So that's, and what am I measuring here? That's inference on one sample. So you take your image, right? You pack it into a ciphertext, and what you want to do is you want to push it through the network, right? We're not learning the parameters here. We're just doing inference. And you want to push it through the network. So it used to be that it would take you half an hour. And now, with our latest implementation, it's taking less than 300 milliseconds. And I think that number is slightly inflated, because that number was from 2 weeks ago, and now it's maybe closer to 250 milliseconds. So, and as I said, like that's really a paradigm shift, because if it takes you 30 minutes, or if it takes you less than 1 second to do inference on one sample, like the realm of possibilities and the use cases that you can have, they're really fundamentally different. Yes. So if I want to be able to talk to you about, you know, the optimizations and the improvements that we are doing with the CKKS scheme at Belfort, then I kind of need to give you an introduction to CKKS and the computational model. So I believe, I mean, you've all seen at least this learning with error framework. So this is like a caricature of a slide. So if you already know what learning with error, then you understand what these slides mean. And if not, then you know you have this secret key, which is here, and that's how you're going to encrypt some value. You're going to add your message, add some noise, and it's believed that if I give you just A and B, then it's difficult to recover S, and it's going to be difficult to recover the message. One thing, I mean, so this is a general slide about learning with error. So in CKKS, there's no rounding here, but it's going to become more clear what the operations are in a few seconds. Because what I want to do is I want to walk you through the process of, you know, I have my data, how do I encrypt it for CKKS computation? So what the idea is that you're going to have one very large vector, think like thousands to 10,000 elements in your vector, and you're going to operate on them, on this vector, like at each position simultaneously. So you take your, you know, your application data, right? It could be a matrix, could be a vector. You pack it into these slots, as we call them, and then you're going to do an inverse DFT. That's going to give you a polynomial, right? So I have my polynomial, and the idea is I want to express this in a way on which I can, so that I can use this learning with error or ring learning with error. So, okay, so, you know, I have my slots. I do this inverse DFT. That gives me a polynomial. What do? Well, this polynomial, it's a real coefficient polynomial. I'm going to do a trick, And I'm going to introduce this delta parameter. So now, and Z0 and the Z, they're integers, right? So I'm going to choose a very large delta so that I can express this as a ratio of two integers. Fine, okay, I introduce a little bit of error, but I already told you I'm kind of okay with a little bit of error. And this delta, you should think of it as something very large. So for the purposes of this presentation, you can think of it as 2 to the 40, right? So 40 bits. And that gives you your message, M. Now, instead of considering M, I'm going to consider delta M. Ah, okay, great. Now I have an integer polynomial. So if I have an integer polynomial, I can consider it modulo a large number, capital Q, and now I can use ring learning with error. Great, so I can do ring LWE encryption and decryption. So my point was, first, when I have my plain text values, I pack them into a vector. I do this, these shenanigans with the delta parameter, which I'm going to call encoding. And then once I have this polynomial, then I can do the encryption. So first encoding, then encryption. Okay, so now I have my encrypted, right? I have this delta, because what did I encrypt? I didn't encrypt M, I encrypted delta M. So now, what do I need if I want to have an FHE scheme? Well, I should be able to both add and multiply ciphertexts, right? So, okay, addition is fine, because I have encryption of delta A plus encryption of delta B is going to be the encryption of delta A plus B. That's just, you know, how linear algebra works. If I want multiplication, then I need that the product of two encrypted messages is the encryption of the product of the messages. And it turns out that this is going to be problematic, so please hold your breath until the next slide. And I'm going to have a third operation, which kind of falls out of the choices that I made from the encoding and the encryption, is I'm going to be able to do rotation on these ciphertexts, right? So I'm going to have an operation that's going to take my encrypted ciphertext, which is what I'm working with. I'm going to apply this rotation operator, and it's going to rotate the slot values, right? So, because those are the things that I want to work on. And so you have addition, multiplication, and rotation, right? So you have you encoded your vector A, B, C, D, and now you rotate all the values and you get B, C, D, A. Great. So, as I told you, I lied a little bit, because if you think about it, right, you have encryption of delta A times encryption of delta B. You do the math, you get this extra delta product. So now what I wanted was delta times A times B, and now I get delta squared. So I'm going to need to do an extra operation, which is going to be to get rid of this delta squared and replace it with delta. And how am I going to do this? I'm going to have what we call the modulus chain, right? So this capital Q, this is the modulus that I'm using, right? When I have my integer polynomial, I consider them integers mod capital Q, and it's a product of smaller primes, and I'm going to take each prime to be roughly 40 bits, right? And when I say that I drop a prime, right? When I divide, what I'm going to do is, what I want to do is I'm going to divide. I want to divide by delta, and what I'm going to do instead is I'm going to divide by one of these qi primes, which, you know, is roughly delta. And again, this introduces noise, but I said that I was okay with this. Of course, if you want to do this properly, you need to manage, you need to compute what is the size of the noise that you carry along, but it turns out that this is not a big problem. And for efficiency reasons, what you're going to do, right? So I told you I have my capital Q, and each QI is 40 bits. So this becomes a very, very large number, right? But I want it to be a large number because I want to be able to drop these QI, right? Because that allows me to do multiplication. So to make this efficient, I'm going to use a residue number system. So I'm going to use the Chinese remainder theorem, and I'm going to have many limbs. And each limb is my big number modulo one of these QI. And that allows me to do the multiplication. And each time I do a multiplication, I lose one of my QI. So I drop one. And so now I have one fewer. And then I do another multiplication, and I have one fewer, one fewer, one fewer, until at the end, I'm going to be at Q0, and I can no longer multiply because I don't have any space anymore to divide by one of the QI. And if I were to do the multiplication, this would introduce a lot of noise and I would lose everything. So what's the trick? Well, what I'm going to do is I'm going to do some accounting. And every time I do a multiplication, I'm going to compute on which level I am. And when I run out of levels, there is this bootstrapping operation, which Walter was also talking about. And the bootstrapping, what it's going to do it's kind of the same idea as in TFHE, but the mechanics is different. But I want to increase my level, right? So I want to go from a ciphertext, which is mod Q0, my last prime, to a ciphertext, which is QL, which is capital Q, which is the full modulus, right? But if I just take my ciphertext and I interpret it modulo this very large number, then I introduce this noise, right? This thing that I don't want, modulo QL. And so I need to do this bootstrapping operation. And that's going to allow me to interpret. It's going to be a very expensive operation that's going to allow me to interpret to increase my levels, basically to reset my levels. And if you look in this big chain of prime that I had shown you to scare you a little bit, you see you have all these 40-bit primes here, and all those that have the comments here, these are the primes that you're using for your bootstrapping. So that means that, I want to do this bootstrapping operation. It's going to give me more levels, but just the fact of doing the bootstrapping operation, I'm going to need to spend levels to do the computation, which is the bootstrapping. So there's actually this Q effective, right? Because if it costs me 12, I bootstrap, 22 levels, it costs me 12 levels to do the bootstrap operation. That means that my Q effective is only 10. So that means that I can do 10 multiplications until I've depleted my levels again, and I need to do another bootstrap. And the game is to try to do bootstraps, as few bootstraps as possible, because bootstrapping is an expensive operation. Okay. Maybe, hopefully, half of you followed me here, and half of you got lost a few slides ago. But if that's you, then you can, reattach yourself to the presentation. Everything's fine. You just need to remember that that we took our plain text values, we packed them in a vector, and the only operations that we're allowed to do are vector addition, vector multiplication, but point-wise, element-wise, and this rotation. But now, so these are the only operations that I'm allowed to do in my computational model. Yeah. So, a few things about hardware, and then I'm going to move on to some algorithmic optimizations that we've been doing. So the platform that we chose to do this work, to do this acceleration, is the GPU, because these ciphertexts, they are quite large, and so that means that you have a lot of memory movement. And just to talk to you about a few optimizations that we've been doing on the GPU. So you have this thing which is kernel, like, okay, maybe I can talk about plain text compression. So you have these plain texts, they're known to everybody, but they can, because of the way that the ciphertexts are packed, you can have like repetitions in these plain texts. And so, but if you already know that you have repetitions in your plain text, then you can reduce the size and expand it later, and that's going to reduce your the data movement on your GPU. Another thing that you can do is kernel fusion. So when you work on the GPU, you have these kernels which are executed, and so kernel fusion is basically to if you chain two operations, you fuse them into a single operation to avoid data movement. Great. So let's go back to, as I promised, the algorithmic improvement. And what I want to talk about is you have this PyTorch model, right? And so how are you going to be able to execute this PyTorch model in FHE? So we're going to encounter three major roadblocks. So, I mean, for those of you who have never seen or written PyTorch, this linear layer, right? We think of a neural network as you have some inputs and some outputs, and then you have some layers in between, which is like vertical, like this. And this linear layer is a matrix multiplication, and this ReLU is an activation function. So let's first talk about what we're going to do with these activation functions, because by definition, they are nonlinear. And so here you have a few examples of activation functions. So for example, this one, which is 0 until 0, and then it's x. So it's the maximum between 0 and x, right? It's this straight line here. That's the ReLU function. But if I get my value in my vector and I want to apply ReLU to it, then I cannot do this, right? Because the only things I can do are addition, multiplication, and rotation. So what's the way out is to do polynomial approximation. So I'm going to, because a polynomial, I can evaluate with only addition and multiplication. And so I'm going to approximate, I'm going to use a polynomial on a bounded interval where it doesn't diverge, it's not too far away from my ReLU function, and that's what I'm going to use for computing the ReLU. But that's going to introduce some error, of course. It's a little bit trickier than this because, first of all, as I said, you're going to need to know the range. So you cannot have a polynomial approximation which is infinitely good over the whole interval, right? So you're going to have to know over what range do I need to approximate my activation function. That's going to be very important. And what's the error that I want to tolerate between my approximation and my ReLU? Of course, and then you're also going to pay a price, because if you want a very good approximation, then you need a higher degree polynomial, and a higher degree polynomial is going to be more expensive to compute. Yes, then there's this concept of escaping activation, right? So if you have a point which is outside the range where you've approximated, then you're going to be in trouble, because then the value that you're going to compute is going to be very different, and then this error is going to cascade to the other layers of the network. Great. So what's the alternative? And this is going to depend on your use case, but you know, there are some model, like let's say you want, as we said, let's say you want to implement ResNet. Well, ResNet has already been trained, it has the weights, right? And you need to, like if in the definition of ResNet you have a ReLU, then you need to evaluate ReLU. So you need to pay this price of the polynomial approximation. But another approach that you could take is you could say, I'm going to not use ReLU, and I'm going to use some other activation function, some other function that I like better. Let's say a quadratic function, right? That's much nicer to evaluate in FHE. And then the question is, if I replace my ReLU with a quadratic function or a degree 4 polynomial, like, will I maintain good ML performance, right? Because if I lose 10% accuracy because I replace my ReLU with a quadratic function, then that might not be a price that I'm willing to pay, right? My performance degrades too much, performance in terms of machine learning metrics. And another point is that it's going to require you to retrain the model because you change the activation function, so you need to change the weights, and that's something that you might not be willing to do because maybe it's very expensive, or maybe you don't have access to the training data. So this is another way to approach the problem, but kind of it depends on the use case. Like you might have people that say, no, I get good results with ReLU, I want to use ReLU, and they don't want to use exotic activation functions. So it's a little bit like, oh, you know, you could use this block cipher and it works much faster, but it's an exotic block cipher. Like you need to convince people that, yeah, it's going to be okay, and some people might not be okay with it. Yes. So that's the first problem that needs to be tackled and that I wanted to highlight. The second one is large matrix multiplications. So I'm going to need to, you know, do these linear layers, and the matrices could be very large. So how am I going to do this? Again, I can only add, multiply, and rotate. So if I use the naive approach to do this, how can I do this? Well, okay, I can take my first row and I encode it, and now I'm going to do the pointwise multiplication between this vector and this vector, because this I know how to do, right? So I get this vector, right, 4 entries. But what I want is I want the inner product of these two vectors, but I don't know how to compute inner product. So I'm going to rotate it once, rotate it another time, rotate it another time, and now I can do the sum of these 4 vectors. And now I get a vector where every entry of the vector is this value. And that's the first entry of my result, right? But now I get this value 4 times, so I will actually need to zero out some of these entries, and I'm going to need to do this for every row. And the point that I want to make is that this is going to be very expensive. It's going to be very expensive in terms of rotations and multiplications, right? Our computational model is that additions can be considered more or less free, but multiplication and rotations are very expensive. So you would like to minimize them. And one way you can do this is you can do a clever packing of this matrix. And you can do what is called the Halevi-Shoup packing or the diagonal packing. And so instead of packing my row-wise like this, I'm going to pack by diagonals. And if you work out the linear algebra, you're going to see that what I can do is I can just rotate my ciphertext, multiply by the diagonals, and if I add these results, then I'm going to get the vector that I'm interested in, right? Which is the matrix vector multiplication. And this turns out to be much cheaper. Okay, the third problem that I'm going to need to overcome, and this is an optimization problem, is where am I going to put my bootstraps, right? Because when I translate my program, I'm going to, right, this is my neural network, right? If it's bigger, where do I put these bootstrap operations so that I put as few of them as possible? And because I don't want to run out of levels. And there are, yes. So again, you're going to get a little bit a feeling of déjà vu because we're going to need a compiler to do this. And the compiler that we're using at Belfort is also Hare. And so this is a Google-led open source project that we're also contributing to. And okay, yeah, I'm also talking about MLIR because, well, I mean, I don't want to repeat everything that Walter said, but it's very nice to be able to use this framework because you get a lot of tools that have been developed by compiler experts. Because, you know, if you want to write a compiler for FHE, you have a new FHE that you want to write a program, right? And you think it's going to go so much faster. The first reflex is that you say, okay, well, I'm going to build my own compiler, and it's going to be so much faster. But then there are all these niceties, right? You need debug framework, you need testing, you need fuzzing, and it's actually very convenient to be able to reuse a framework that has been developed by experts and people who know about compilers. And this MLIR framework, I mean, we've put a few projects here that use it. So these are like really large-scale projects, and they rely on this MLIR framework. So it's a little bit like standing on the shoulders of giants, right? So what's the framework that we want to use, right? So this is so the one that we want to support is PyTorch. So you write your PyTorch. Then there are some libraries to take your torch model and convert it to MLIR. That's part of the LLVM project. And then most of what's going to happen is going to be in this linalg, so that's for linear algebra, dialect. And that's what Hare is going to take as input. And that's what it's going to convert to, it's going to compile to some output dialect. So what does it look like? You've seen this slide before, but you know, you can annotate which scheme you're using. So in our case, it's CKKS. You can say which input is secret. We're going to care about these polynomial approximations. So you can say over what range do you need to do these polynomial approximation. And these ranges, you need to compute them. So what we're going to do, so what we're doing at Belfort is you push some test data through the network, some representative data, and you can have PyTorch remember what are the ranges for all the layers, and then you can annotate it and you can pass this information to, you can write it in MLIR, you pass it to Hare, and then Hare has the information to be able to pick the right polynomial approximation for this. So this is, I mean, again, the same dialects that you've seen in the previous presentation because it's the same framework, but torch to MLIR to the secret arithmetic to the scheme, and then you can exit. And usually, if you write CKKS, it's going to be Latigo or OpenFHE are going to be your target libraries. But now you can also target the Belfort GPU, the Belfort FPGA, and eventually the Belfort ASIC as well. And what is very nice about this model is that, if you have some, the Belfort GPU, maybe it knows very well how to do this matrix vector multiplication, because it's going to keep all the data resident on the GPU. It's going to avoid memory transfer between the GPU and the host, and it's going to do all sorts of optimizations. So what you can do in this compiler is you can annotate some operation, and you say, this one, don't touch it. It's fine. I'm just going to pass it straight through to the GPU, and you're going to get a result, and then you can compile the rest of the program. So it's very modular, and it allows you to write something which is very generic, but not lose too much performance. Yes, so let me talk about applications. So I've picked 3 applications that I wanted to highlight today. So the first one is this facial spoofing. So what's the idea here is, you have Face ID on your phone or on your laptop, and when it sees you, it unlocks the laptop. But an attack on this is that you take a picture of your friend's. You take a picture, you print it, and you show it in front of the laptop, and then it unlocks the laptop, right? But so facial spoofing prevention, the idea is that you want a model that's not going to do facial recognition. It just wants to recognize if this is a real person standing in front of the camera or if it's a printed image, for example. And then if you pass this facial spoofing detection, then you will move on to a real face detection algorithm. And the reason why FHE is a good fit for this is because you really want to run it on the server, because the people who run the model, they don't want to put the model on the client device, because if you put it on the client device, people can inspect it, and if they know what the network is, then they will work to reverse engineer it. So actually you want to prevent that, so you keep the model on the server. So this is actually a very nice use case, because you have the client who needs to encrypt her data because it's private, it's like facial data. You don't want to share it with anybody, but the server also doesn't want to share the model. So this one is a neural network. So this is neural network inference again, and so this is particularly well suited for CKKS. Another use case that we have which is using TFHE is this pseudonymization. So if you saw this morning, there was a presentation by Frank Robin that was talking about this. So you have, in the healthcare sector, you need to do pseudonymization. So you have an ID and you would like to link it to the pseudonym, but you would like people not to be able to do the link between the two. So you can do this with FHE and third party, and nobody can link between the ID and the pseudonym. That's another proof of concept that we're working on at Belfort, and this one uses TFHE. And finally, the one that I want to dive into is another one with CKKS, and it's for predictive maintenance. So for those of you who haven't heard of predictive maintenance, you can imagine a large operator that has many machines that require maintenance, and you would like to know which machine should I repair, which machine needs maintenance before it breaks down, right? Because the cost of breaking down could be very large, and then you need to replace it instead of repairing it. So again, so this is another example where we're using neural network inference. And so the use case works like this. So you have this plant operator, right, which has many machines, and then it's collecting sensor data from these machines and encrypting them, sending them to a server which is going to run some neural network inference on this. And you consider that this model, it's the manufacturer of these devices that knows this model and that is operating it. But the plant operator doesn't want to share this precious sensor data because that would reveal something about his operation. And the manufacturer doesn't want to reveal the machine learning model. So then they can run it here using FHE, send it back to the plant operator, and then the plant operator gets this metric about how much useful life is left for each device, and they can take appropriate measures and decisions about which machine should be replaced. So this is a demo project that we're working on with NXP. Again, so it's a convolutional neural network, which is particularly well suited for CKKS, because a convolution, you can see it as a linear operator. So this makes things handy. And yes, so you have convolution layers, activation layers, you have pooling, so putting many pieces together, and matrix multiplication. So yeah, here I've put like a few models that have been executed in FHE, in CKKS. So at the beginning, we were doing only, logistic regression, and then more and more the models got bigger and bigger and can do more and more, and you make them go faster and faster, and so we're kind of attacking and running bigger and bigger models. And to be able to do this, right, so if you remember my benchmark slide from the beginning, to be able to go from 2 or 3 hours down to 300 milliseconds, then we really need to make improvements all across the stack. And to be able to do this, we need expertise at many different levels. And so that's us, that's Belfort, and that's what we're working on. We want to make FHE go fast so that it can be used in more cases. And that's all I have to say today. So thank you.